Next in magnetism, we're going to go beyond just charges in magnetic fields to current-carrying wires in magnetic fields. So let's say that this is a wire with some current running through it, so I've got a current that way. We're going to find out if, say, I put a magnetic field in this direction with that wire, what would happen. So first thing you have to know is that in circuits, we being physicists, consider current to be the way that a proton would flow. Now that's weird because it's not actually the protons that are moving. But what happened was, we knew about electricity before we really understood how electrons were working to cause electricity. And so when we were originally coming up with how circuits worked, most physicists and engineers thought, oh, well, protons or positive charges are moving from here. So they wouldn't have called them protons at the time. They would have just thought positive charges were moving from the positive side of the battery to the negative side of the battery. Now we now know that it's actually the electrons that are moving. So electrons are actually moving from the negative to the positive side. But since we physicists came up with current before discovering how electrons worked exactly, it's still by convention that we say current flows from positive to negative. Now this is really convenient when it comes to the right-hand rule for magnetism, though, because current describes the way a positive charge should move. We can just consider current to be velocity of a positive charge. So if I were to solve this problem and do the right-hand rule, my velocity would be in the same direction as my current. So I would then say, okay, current is telling me positives are moving that way, even though we know that's not true. The positives are not the things moving, it's the negative, it's the electrons moving through the wire. But the physics works the same. We can pretend that since electrons would be moving the opposite way, remember you just flip the right-hand rule when you're dealing with electrons, so since electrons will be moving the opposite way, it's okay to say that protons, for the purposes of the right-hand rule, it's okay to pretend like the positive charges are moving that way. And so your current gives you the direction of your velocity. So in doing the right-hand rule for F equals QV cross B, my V would be in the direction of the current. Direction of current. And so here, my V would be to the right because that's the direction we've said the current is. So V to the right, I'm doing the right hand. Magnetic field pointing up here, which means my magnetic force on that wire would point out of the page. So I did V to the right because that's the way the current's going. B up, force points out. So basically the big takeaway is when we throw in wires, the current, you'll use its direction as your velocity because it's telling you which way positive moves, and then you don't have to flip it. Even though it's actually the electrons that are moving, we've already done the flipping by pretending the protons or positive charges are moving the opposite way. So that kind of that opposite part is where we've already flipped the right-hand rule for it. And if you checked it, if you did, okay, so electrons moving to the left, pointing left with my right hand, magnetic field pointing up, now I get into the page, but since those are electrons, I have to flip my right-hand rule, and I get out of the page. And so that's the same thing I got by pretending that the protons were moving to the right instead of the electrons moving to the left. And if you're wondering how I'm deciding protons move to the right, that was the direction of my current. It tells me which way the positives should move. And so what this means is if you had that wire and you suddenly ran a current through it, it would fly towards you, fly out of the page, because that's the way the force on it would be. Some pretty powerful examples, actually, you're going to get to see in class tomorrow of what happens to wires in magnetic fields.